Welcome to Astro Odyssey. Explore the universe. Imagine, for a moment, the sheer physical presence of your own existence. You are not floating. You are standing, your feet pressed firmly against a surface that resists you. A floor made of wood, concrete, or steel. That floor is part of a building. A carefully assembled structure that rises against gravity, only because countless forces are in perfect balance. Beneath that building lies soil, rock, tectonic plates, layers of matter stacked over billions of years. All of it is pinned in place by a force you cannot see, cannot touch, and rarely think about, yet feel constantly. Gravity. It is the invisible hand that keeps your body anchored, that stops the air from drifting into space, that binds oceans to continents and continents to the planet itself. Within this grounded perspective, your intuition about size feels reliable. A mountain appears immense because, at human scale, it is immense. It rises kilometers into the sky, cutting through clouds, altering weather, dominating the horizon. To climb one is an act of endurance. Hours or days of physical exertion are required just to reach a single summit. Mountains feel eternal, immovable, older than memory. They become symbols of permanence, of obstacles that cannot be ignored or easily overcome. To a human standing at its base, a mountain feels like the upper bound of large. But scale is a trick of perspective. Step into an airplane, rise just a few kilometers above the surface, and the illusion begins to crack. From the window, that same mountain loses its authority. The jagged peaks smooth out, the dramatic vertical rise compresses into subtle ridges. What once felt overwhelming becomes a mere wrinkle in the Earth's crusted texture, not a titan. Go higher still, into orbit, and the mountain disappears entirely, erased into the planet's curvature. The thing that once dominated your entire field of view, no longer even qualifies as a feature. This is the first fracture in our understanding of significance. What felt immense was only immense relative to you. The mountain never changed. Only your vantage point did. Size, it turns out, is not an absolute quality. It is relational. It depends entirely on where you stand and how far back you are willing or able to look. And if something as monumental as a mountain can be reduced to a trivial detail by a small shift in perspective, then the question becomes unavoidable. What else do we believe is enormous, simply because we have never stepped far enough away to see it properly? If we continue pulling back, the Earth itself begins to suffer the same fate as the mountain. At ground level, the planet feels infinite. Oceans stretch beyond the horizon. Continents span thousands of kilometers. Entire civilizations live and die without ever crossing its surface. The Earth feels like the ultimate container, everything that has ever mattered to us wrapped into one vast, self-contained sphere. Its size feels unquestionable. Its importance absolute. But in space, the illusion collapses quickly. Seen from afar, Earth is revealed as what it truly is. A rocky sphere, roughly 12,000 kilometers wide. Suspended in darkness. Its iron core, molten mantle, and fragile crust are suddenly finite, measurable, bounded. Place it next to Jupiter, and the comparison becomes humiliating. Jupiter is not just larger, it is overwhelmingly larger. Its mass could swallow Earth's whole without effort, reducing our planet to the status of a decorative pebble. Side by side, Earth looks like a marble pressed against a basketball, a toy beside a monument. Then comes the sun, and with it, the true beginning of insignificance. The sun is so vast that language begins to fail. Over 1 million Earths could fit inside its volume, and even that number is abstract to the point of meaninglessness. Try to imagine stacking 1 million planets, oceans, cities, mountains, and all inside a single sphere of plasma. And your intuition simply gives up. The sun is not just larger than Earth. It exists on an entirely different tier of reality. Earth is no longer a world. It is debris. At this point, something unsettling happens. The Earth stops feeling like a place and starts feeling like a rounding error. In the scale of the solar system, our entire planet becomes an afterthought. A minor fluctuation in mass around a star that does nearly all the gravitational work. Every war, every culture, every love story, every tragedy compressed into something so small it barely registers. This is the first true level of the Speck realization. Not that humans are small, that idea is easy to accept, but that our entire world, the stage upon which all of human history has played out, is itself insignificant when viewed from a broader cosmic context. The Earth is not the centerpiece of the solar system. It is a footnote. And if that is true here, within our own celestial neighborhood, then the implications of looking even farther out become profoundly disturbing. Yet even the sun, for all its overwhelming dominance, is merely one star among billions. When we look up at the night sky, what we see feels infinite. a scattered ocean of light, stretching endlessly in every direction. To the unaided eye, the stars appear evenly distributed, a celestial wallpaper that surrounds us completely. It feels as though we are standing at the center of something vast, gazing outward into an immeasurable expanse. But this too is an illusion born of limitation. Every star you can see without a telescope, every pinprick of light that has ever inspired poetry or guided sailors, is located within a relatively tiny neighborhood surrounding our solar system. This region is not the galaxy at large. It is a small bubble, a local sampling biased heavily toward proximity and brightness. The Milky Way extends far beyond what human eyes can naturally perceive. Its true scale, hidden behind distance, dust, and the finite sensitivity of our vision. In reality, we are tucked away in one of the Milky Way's quieter suburbs, a modest spiral arm, far from the galaxy's dense core and far from its outer extremes. From here, the galaxy stretches outward in a flattened disk, roughly 100,000 light-years across. To grasp what that means, consider that light, the fastest thing in the universe, travels at 300,000 kilometers per second, yet would still require 100,000 years to cross from one side of the Milky Way to the other. Every photon you see tonight began its journey long before recorded human history even started. At this scale, human concepts of distance collapse. Kilometers and miles become laughably inadequate. Even years fail, forcing us to invent new units, light years, just to keep the numbers manageable. And still, the magnitude resists comprehension. The Milky Way is not something you travel across. It is something you exist inside of, embedded so deeply that you cannot see its edges from within. What once felt like an infinite sky is revealed to be a tiny window, offering a narrow view from an obscure corner of a much larger structure. We are not observers standing outside the galaxy, admiring it from afar. We are dust motes suspended inside it, glimpsing only what lies close enough to shine brightly through the dark. For most of human history, the Milky Way represented the absolute ceiling of imagination. It was the final boundary, the largest structure that could plausibly exist, containing hundreds of billions of stars, each potentially hosting its own system of planets. The galaxy felt inexhaustible. Even today, when we say the Milky Way contains roughly 400 billion stars, the number is not something we truly understand. It is something we recite, not something we visualize. The human brain evolved to navigate landscapes measured in kilometers, lifetimes measured in decades. It did not evolve to intuitively grasp distances measured in tens of thousands of light years or populations measured in hundreds of billions. Numbers at this scale stop functioning as quantities and become symbols instead. 100,000 light years does not describe a distance so much as it announces defeat. It is a signpost that says, beyond this point, imagination fails. So we reach for language. We say gargantuan, colossal, unfathomable. We stack adjectives on top of one another in an attempt to bridge the gap between numbers and feeling. But the words feel hollow, inadequate. They bounce off the reality they are meant to describe. The Milky Way remains stubbornly beyond emotional comprehension. Its true vastness, locked behind abstractions and equations. In this way, the galaxy becomes effectively infinite, not because it truly is, but because the difference no longer matters to us. Whether something is 100,000 units wide or 1 million units wide makes little emotional difference once both numbers are far beyond lived experience. The Milky Way becomes a conceptual horizon, a place where curiosity slows, not because answers are lacking, but because the scale itself is exhausting. And for a long time, that was enough. The Milky Way felt like a reasonable upper limit, a structure so large that nothing bigger seemed necessary or even possible. It satisfied our need for cosmic grandeur, while still allowing us to feel that we understood our place within it. That sense of comfort, however, was temporary and deeply misleading. The universe, it turns out, has no obligation to respect the limits of human comprehension. Beyond the familiar glow of stars lies the intergalactic medium, a cold, sparse vacuum threaded with faint filaments of gas and dark matter. This is the realm between galaxies, where distances stretch not in thousands, but in millions of light. It is here that the Milky Way begins to look less like a grand island of light and more like a flicker-one spark, among countless others scattered across a cosmic abyss. In this environment, scale becomes brutal. Entire galaxies are reduced to points. Clusters of galaxies form cities of light, bound together by gravity across unimaginable distances. And even these clusters are merely nodes in something larger, the cosmic web, an immense invisible scaffolding that organizes matter on the largest scales known to physics. Compared to these structures, the Milky Way is not impressive. It is ordinary. For centuries, Astronomers believed they had identified the universe's upper limits. We catalogued massive galaxies, enormous clusters, and vast voids, assuming that somewhere, physics would draw a firm line. Gravity, expansion, and energy constraints would surely prevent structures from growing beyond a certain size. There had to be a maximum cosmic stop sign where growth became impossible. That belief was comforting. It suggested order. It implied that, while the universe was vast, it was still governed by boundaries we could eventually map and understand. We were comfortable believing we had found the monsters of the deep and that no larger beasts remained undiscovered. Comfort, however, is often just ignorance, wearing a reassuring mask. Because beyond what we had already named and measured, there existed structures that did not care about our assumptions. Structures that did not fit neatly into our models. Structures so large that they did not merely challenge our theories, they humiliated them. And it was only a matter of time before our instruments became sharp enough to force us to confront just how wrong we had been. For a long time, astronomers believed the universe enforced strict architectural rules. Galaxies, we assumed, could only grow so large before the laws of physics intervened. Gravity could gather matter. Yes, but only up to a point. Beyond that, competing forces would tear structures apart. The expansion of the universe would stretch them thin. Energy requirements would become unsustainable. There had to be a ceiling, a hard upper limit dictated by nature itself. This assumption felt reasonable. After all, we saw patterns everywhere we looked. Galaxies tended to cluster within a predictable range of sizes. Their shaped spirals, ellipticals, irregulars followed recognizable categories. Even the most massive examples we could observe still obeyed a sense of proportion. They were big, yes, but not absurdly so. They fit comfortably within our models, so we pointed to galaxies like M87 or the Great Sombrero and declared them champions. These were the titans, the skyscrapers of the cosmos. Their immense mass and energetic cores seemed to represent the pinnacle of what gravity could assemble before chaos took over. In our minds, the universe was impressive but oddly wild, yet restrained. This mindset was deeply anthropocentric, though we didn't recognize it at the time. We mistook the limits of our observations for the limits of reality itself. Like ants gazing up at a single skyscraper, we assumed nothing taller could exist, simply because we had never seen it. Our theories became comfortable echoes of our ignorance. The idea of a maximum galaxy size was especially appealing because it suggested finality. It implied that cosmic growth had boundaries, that there were rules even giants had to obey. This made the universe feel more understandable, more tame, a place where scale, while enormous, was still ultimately manageable. But the universe has never been interested in comfort. The limits we believed in were not laws of nature, they were artifacts of our tools. And once those tools improved, once our reach extended beyond what the eye alone could perceive, the assumptions we had built entire frameworks upon began to crumble. The hard cap we thought existed wasn't a ceiling at all. It was a blindfold. The transformation began quietly, not with a single discovery, but with a shift in how we looked. For most of history, astronomy was constrained to the narrow sliver of reality visible to human eyes. Optical light colors we evolved to see was our primary window into the cosmos. Stars were points. Galaxies were smudges. The universe, though vast, appeared neat and well-contained. Then our eyes changed. As technology advanced, we learned to observe the universe in wavelengths far beyond vision. Infrared revealed hidden stars cloaked in dust. X-rays exposed violent regions near black holes. But it was radio astronomy that truly shattered our assumptions about scale. Radio waves, with their long wavelengths, revealed structures that optical light simply could not trace. Structures too diffuse, too ancient, or too energetic to glow visibly. When the sky was viewed through radio eyes, it became haunted. Ghostly outlines emerged where nothing had appeared before. Vast lobes of energy floated between galaxies. Ancient explosions left behind fading echoes. Black holes revealed themselves not as silent voids, but as engines feeding, erupting, and reshaping their surroundings on colossal scales. Unlike stars, radio structures did not respect tidy boundaries. They sprawled, they leaked, they stretched far beyond the luminous core that optical telescopes had trained us to think of as the galaxy. The universe suddenly looked less like a collection of isolated islands, and more like a battlefield, scarred by jets, shocks, and colossal outflows of energy. This new perspective forced an uncomfortable realization. We had been underestimating everything. The neat, circular galaxies we admired were only the bright hearts of far larger systems. What we had called empty space was anything but empty. It was alive with motion, energy, and the long-lasting consequences of events, billions of years old. Radio. Astronomy didn't just add detail, it rewrote the map. It revealed that galaxies were not static objects, but active participants in shaping the universe around them. And once that door was opened, it became inevitable that we would find something that broke the scale entirely. It was during this quiet revolution that something deeply unsettling appeared in the data. Researchers using the low-frequency array, or LOFAR network of radio antennas spread across Europe were surveying the sky with unprecedented sensitivity. LOFAR didn't look for beauty. It looked for whispers, faint emissions, stretched thin across vast distances, barely distinguishable from background noise. In one unremarkable patch of sky, roughly 3 billion light-years away, those whispers formed a shape that shouldn't have existed. At first it didn't look like anything special, not a bright point, not a dramatic flare, just a smear-on, extended, diffuse signal spread across an absurd region of space. But the longer the researchers stared, the more disturbing it became. The signal was too large, too coherent, too structured to be a coincidence. This wasn't a glitch. It wasn't interference. It was real. As measurements refined, the scale of the structure emerged, and with it, disbelief. Existing models of galaxy growth could not account for something this enormous. The signal extended far beyond the boundaries where galactic influence was supposed to fade. It occupied a volume of space so vast that it made even large galaxy clusters look compact by comparison. The data forced a choice. Either the measurements were wrong, or our understanding of how galaxies evolve was incomplete. There was no comfortable middle ground when independent confirmations arrived. Doubt evaporated and was replaced with awe and unease. This was not just a large galaxy. It was something categorically different, something that had grown, uninterrupted for billions of years, in defiance of expectations. What LOFAR had uncovered was not merely an object. It was a question mark written across millions of light-years of space. They named it Alcyoneus, after the giant of Greek mythology, who challenged the gods themselves. The name was not poetic exaggeration. It was a warning. Alcyoneus was not just breaking records. It was challenging the conceptual framework we use to describe the universe. This was no ordinary galaxy. At its center lay a relatively unremarkable host. Galaxy, something that, on its own, might never have drawn attention. But extending from that modest heart were colossal structures unlike anything previously observed. Twin lobes of radio-emitting plasma stretched outward in opposite directions, forming a cosmic span so vast it bordered on the absurd. Alcyoneus was not luminous in the way stars are luminous. Its presence was revealed through energy, not light, through motion, not form. It was a structure defined by interaction between black holes and space itself, between matter and the cosmic web that cradles all large-scale structure. In this sense, Alcyoneus was not merely a galaxy. It was an event stretched across time, a record of sustained activity, of jets launched from a black hole and allowed to travel almost unhindered through the intergalactic medium for billions of years. Its existence forced astronomers to rethink how energy propagates across the universe. How far can a black hole's influence truly extend? How gently or violently must the surrounding environment behave to allow such growth? Alcyoneus didn't just sit within the cosmic web, it exploited it, threading its energy along the universe's largest structures like veins carrying fire. This was no passive giant, it was an architect of scale. To truly understand the size of Alcyoneus, metaphor becomes unavoidable. Numbers alone collapse under their own weight. 16 million light-years is not a distance, it is an insult to intuition. So instead, we return to the Speck realization, now in its final and most brutal form. Imagine shrinking the Milky Way, every one of its 400 billion stars, every nebula, every black hole, down to a single pixel on your screen. One dot, barely visible. Now imagine Alcyoneus not as another pixel, but as something so large that it doesn't fit on the screen at all. It spills beyond it. It fills the wall behind the screen. It dominates the room you are sitting in. This comparison is not poetic license. It is proportionally accurate. At this scale, familiar reference points disintegrate. The Milky Way ceases to feel grand. It becomes a unit of measurement, a ruler used to describe something far larger. Our galaxy, once the crown jewel of cosmic imagination, is reduced to a footnote in the description of a true behemoth. The Speck realization is complete when you understand this. There are structures in the universe so large that everything you have ever known exists not merely inside them, but so far below their scale that comparison itself becomes uncomfortable. Alcyoneus is not impressive because it is big. It is impressive because it reveals just how small our former definitions of big truly were. And once that realization sets in, there is no going back. Numbers alone cannot prepare you for the size of Alcyoneus, but they are unavoidable. This single structure spans approximately 16.3 million light-years from end to end. That number is not impressive in the way a mountain is impressive, or even in the way a galaxy is impressive. It is impressive in a way that actively resists understanding. A light-year itself is already a hostile unit for the human mind. The distance light travels in a full year, racing through space at 300,000 kilometers per second without ever slowing down. Multiply that by 16 million, and meaning begins to evaporate. To regain some footing, we reach for comparison. The Andromeda Galaxy, our nearest major galactic neighbor, lies about 2.5 million light-years away from the Milky Way. This distance is so vast that the two galaxies have spent billions of years drifting toward each other, destined to merge in the distant future. For most astronomical discussions, that separation is enormous, cosmically significant, almost intimidating. Alcyoneus makes it trivial. You could place the entire distance between the Milky Way and Andromeda inside Alcyoneus 6 times over and still have room left. 6 copies of one of the most famous intergalactic gulfs we know, swallowed by a single structure. At this point, large stops being descriptive and becomes misleading. Alcyoneus does not merely occupy space, it dominates it. It stretches across regions of the universe that are otherwise sparsely populated, filling voids that would normally separate entire galactic communities. What makes this especially unsettling is not just the size itself, but how casually it exists. There is no explosion marking its boundaries, no sharp edges. It simply extends quietly, persistently, until it reaches distances where most structures would have faded into irrelevance. It is not a compact object. It is a sprawl, a cosmic overreach that ignores our expectations of proportion. Alcyoneus forces a recalibration of scale. Distances we once treated as meaningful reference points are demoted to internal features. The universe has not grown larger. Our sense of what counts as large has collapsed. This is not a gradual realization. It is a sudden one. Like discovering that the map you've been using was printed at the wrong scale all along. When we speak of Alcyoneus, we are not speaking of a typical galaxy scaled up to absurd proportions. We are speaking of something fundamentally different, a member of a rare and extreme class known as giant radio galaxies, or GRGs. These objects are not defined by their stars, nor even primarily by their mass. They are defined by energy, reach, and persistence. A standard galaxy is a gravitational ecosystem. Stars orbit within a dark matter, halo gas forms new suns, and everything remains bound within a relatively compact region of space. A GRG, by contrast, is a hybrid entity. At its center lies a conventional galaxy, modest and unassuming, but extending far beyond that luminous core are colossal radio-emitting lobe structures so large, they blur the line between galaxy and environment. These lobes are not passive halos. They are the scars of long-term activity, inflated by jets launched from a supermassive black hole at the galaxy's center. In GRGs, those jets do not quickly dissipate or collapse. Instead, they survive, travel, and expand over millions of light-years, interacting with the intergalactic medium itself. In this way, a giant radio galaxy is less like a city and more like an empire. Its influence extends far beyond its borders. It reshapes the space it occupies, compressing gas, altering magnetic fields, and injecting enormous amounts of energy into regions that would otherwise remain cold and inert. Alcyoneus represents the absolute extreme of this phenomenon. It is not merely large by GRG standards, it redefines them. Its central galaxy is almost irrelevant compared to the scale of its lobes. If the stars were removed entirely, the structure would still exist visible in radio waves alone, an enormous, invisible monument to sustained cosmic violence. Calling Alcyoneus a galaxy is technically correct, but emotionally misleading. It is more accurate to think of it as a system one that bridges the gap between discrete objects and the large-scale structure of the universe itself. It belongs to the alphas of cosmic architecture, rare, dominant, and indifferent to human intuition. The true source of Alcyoneus's size lies in its wings, its vast radio lobes, stretching outward like the limbs of a sleeping titan. These lobes are not made of stars or planets, but of plasma, a diffused, electrified soup of particles energized to extraordinary levels. Their origin traces back to the galaxy's center, where a supermassive black hole acts not as a consumer, but as an engine. As matter spirals into this black hole, it does not all disappear. A fraction is redirected, accelerated, and launched outward along magnetic field lines at speeds approaching that of light. These jets are narrow, focused, and devastatingly energetic. They are not brief outbursts, but sustained processes that can persist for hundreds of millions or even billions of years. In Alcyoneus, these jets have enjoyed ideal conditions. The surrounding intergalactic medium is thin, offering little resistance. The environment is calm, free of violent collisions that might disrupt the flow. As a result, the jets travel enormous distances before slowing, inflating gigantic lobes where their energy finally disperses. This is not fire in the familiar sense. There is no flame, no heat you could feel. Instead, it is electromagnetic fury, electrons whipped to relativistic speeds, magnetic fields stretched and twisted across intergalactic space. The lobes glow faintly in radio wavelengths, invisible to human eyes but unmistakable to sensitive instruments. What is most unsettling is how empty these lobes are. They span millions of light years, yet contain almost nothing. No stars, no planets, just energized particles and magnetic fields, marking the passage of a black hole's influence across cosmic time. These structures persist long after the central engine quiets, lingering like after images burned into the fabric of space. Itself, Alcyoneus is not large because it collected more matter than other galaxies. It is large because it refused to stop speaking, broadcasting its presence into the void for billions of years, until the universe itself became its canvas. To visualize what Alcyoneus has done, imagine a pressure washer fired into a vast, undisturbed snowfield. The jet carves a narrow channel, pushing forward relentlessly, until it reaches a point where resistance causes the water to spread outward, mushrooming into a wide, bulbous shape. Over time, the disturbed region grows far larger than the initial stream itself. Alcyoneus has been performing a similar act on a cosmic scale. Its jets pierce the thin gas between galaxies, carving twin tunnels through the intergalactic medium. Where the jets slowed, their energy spread outward, inflating enormous lobes that continued expanding long after the initial momentum dissipated. This process repeated, continuously, over immense spans of time. What makes this extraordinary is the duration. Many galaxies produce jets, but few sustain them long enough to build something like this. Alcyoneus did not erupt once and fade. It remained active, patient, persistent. It claimed territory not through speed, but through endurance. The result is a structure so large it dwarfs entire galaxy clusters. Regions that should be dominated by gravitational interactions between hundreds of galaxies are instead filled by the faint glow of Alcyoneus's lobes. It does not just exist within the cosmic landscape. It overwrites it. This expansion also tells us something unsettling about the universe itself. It suggests that the intergalactic medium, in some regions, is calm enough to allow such structures to grow unchecked. The universe, at least locally, is quieter and emptier than we once believed. Empty enough for giants to stretch out and sleep. Undisturbed. Alcyoneus is not a freak accident. It is proof of concept. Proof that under the right conditions, scale has no obvious upper limit. That energy, given time and space, can write signatures across distances we once thought untouchable. The most disturbing question raised by Alcyoneus is not how it formed, but whether it has finished forming at all. What we see is a snapshot frozen in time and image of the galaxy as it existed 3 billion years ago, because that is how long its light took to reach us. The universe has not stopped since then. In the present cosmic moment, far beyond our observational reach, Alcyoneus may be larger still. Its jets could have continued expanding. Its lobes could have grown broader, dimmer, more diffused. Entire additional millions of light years may now lie between its extremities. There is no guarantee that what we observe represents its final size. We may be seeing it mid-breath. This temporal disconnect is deeply unsettling. We like to think of observation as passive, as witnessing reality as it is. In astronomy, observation is archaeology. Every image is a fossil. Alcyoneus is not a giant we are watching grow. It is a giant we are glimpsing long after the moment has passed. That realization introduces a quiet dread. If structures like this can exist, persist, and grow beyond our ability to monitor them in real time, then the universe is not a static gallery of objects. It is a living system, full of slow, unstoppable processes that operate on timescales far beyond human relevance. Alcyoneus reminds us that cosmic history does not pause for comprehension. Giants rise, stretch, and fade, regardless of whether anyone is watching. We arrive late, measure what remains, and try to reconstruct the story. And in doing so, we are forced to confront a humbling possibility. The largest things in the universe may never be fully known, not because they are hidden, but because they are still unfolding. There is a particular kind of existential unease that emerges when scale becomes too large to process. It is not fear in the traditional sense. Nothing is threatening you directly, but a quiet destabilization of meaning. We are comfortable with the idea that the universe is big. What unsettles us is realizing that it is big in ways that make our usual frameworks for order feel naive. We tend to imagine the cosmos as a structured place, beginnings followed by middles, causes followed by effects, systems that grow and then stop. Even chaos, in our minds, follows rules. Alcyoneus disrupts this comfort. Its size and persistence suggest that the universe does not always obey the tidy narratives we prefer. Some processes do not resolve. Some structures do not neatly conclude. They simply continue, expanding until the environment no longer allows them to do so. Human history, by comparison, collapses into new. Entire civilizations rise and fall in spans of time that would register as a rounding error. Against the lifespan of Alcyoneus's jets, empires, languages, religions compressed into moments so brief they are effectively invisible on a cosmic timeline. This is not an insult to human achievement, but a reframing of scale. Meaning does not disappear. It shrinks. Alcyoneus stands as a monument to forces that do not care about narrative closure, gravity and electromagnetism, working patiently and relentlessly. Sculpted a structure that dwarfs our capacity for intuition. There was no intention behind it. No design, just physics, given time and emptiness. This realization can feel disorienting. If the universe can produce something so vast without purpose, then where does that leave us? The discomfort arises not from insignificance itself, but from the sudden absence of a cosmic center. Alcyoneus reminds us that the universe does not revolve around observers. We are not the axis of scale or importance. We are participants in a system that operates just as effectively without us. And yet, in confronting that truth, we gain a clearer view of reality, one stripped of comforting illusions, but richer in honesty. To truly grasp the loneliness of Alcyoneus, imagine standing not at its center, but within one of its immense radio lobes. There would be no stars nearby. The host galaxies, the birthplace of the jets that formed this structure, would be so distant that its combined light would fade into invisibility. You would be suspended in a vast, silent expanse of energized plasma, millions of light years from anything resembling a familiar landmark. This is not the dramatic emptiness of science fiction, filled with glowing nebulae and brilliant suns. It is a subtler void, dark, sparse, almost entirely devoid of matter. The plasma around you would be thin beyond intuition, less dense than any vacuum we could create on Earth, yet still structured, shaped by magnetic fields stretched across distances that mocked comprehension. In every direction, the same nothingness would extend. No horizon, no edge, just space, continuing outward until even the memory of structure dissolves. And yet, despite this overwhelming emptiness, you would still be inside a galaxy, not metaphorically, but literally. This desolation would count as part of a single, coherent cosmic object. That contradiction, being surrounded by almost nothing, while technically remaining within something immense, is deeply unsettling. It exposes how poorly human intuition handles scale. We associate belonging with proximity, with density, with visibility. Alcyoneus violates all of those assumptions. The loneliness of such a place is not emotional. It is structural. It is the loneliness of distance itself, of energy spread so thin that interaction becomes rare, of time stretched so long that change feels hypothetical. This is not a place where events happen quickly, or at all. It is a place defined by persistence, not activity. Standing there, you would confront a universe that is not hostile, but indifferent. Nothing would acknowledge your presence. Nothing would respond. The silence would not be threatening. It would simply be complete. We often describe things as terrifyingly large without meaning it literally. Usually, it is hyperbole, a way to emphasize surprise, or, with Alcyoneus, the phrase becomes precise. Its size is not just impressive, it destabilizes the mental scaffolding we rely on to make sense of existence. For centuries, the Milky Way occupied the role of cosmic giant in our imagination. It was our great home, vast enough to inspire wonder, while still feeling like something we belonged to. Alcyoneus shatters that illusion. It reveals that our galaxy is not a dominant structure, but a modest island in a universe ruled by far larger entities. The shift is uncomfortable because it mirrors a familiar human experience. We all grow up believing our immediate surroundings are central, only to discover they are small pieces of a much larger world. Alcyoneus forces that realization on a cosmic scale. The Milky Way is no longer the city. It is the village, quaint, self-contained, and largely unaware of the vast sprawl beyond the horizon. This does not make our galaxy less beautiful or less important. It reframes its role. The Milky Way is not diminished. It is contextualized. Its grandeur exists. But it exists alongside and beneath structures of a magnitude we never anticipated. What makes this realization powerful is that it is not speculative. Alcyoneus is not a theoretical construct or a hypothetical extreme. It is real, measured, observed. Its presence is a reminder that the universe contains layers of scale we have only just begun to uncover. And if one such titan exists, there may be others. Or worse, there may be even larger structures waiting beyond the reach of our current instruments. Structures that would make Alcyoneus itself feel provincial. Confronting this scale has a strange side effect. It alters the emotional weight of human concerns. In a universe where a single galaxy can stretch for 16 million light-years, the dramas that dominate our daily lives begin to feel lighter, not meaningless, but less absolute, less permanent. This shift is not nihilistic. It does not erase love, ambition, or suffering. Instead, it reframes them. Our conflicts matter deeply to us because we experience them intimately, not because they echo across the cosmos. Alcyoneus does not invalidate human meaning. It reveals that meaning was never dependent on cosmic size to begin with. We are not central characters in the universe's story. We are not even background characters. In purely physical terms, we are just temporary arrangements of matter on a small planet orbiting an average star. That realization can feel brutal at first, like a stripping away of importance. But there is freedom in it. If we are not cosmically significant by default, then significance becomes something we create. Meaning is no longer bestowed by scale or destiny. It emerges from connection, from experience, from consciousness itself. The universe does not care about our stories, but we do, and that is enough. Alcyoneus places us firmly in perspective. It tells us, without malice, that the universe is not built around us, and in doing so, it quietly invites us to stop demanding that it be. And yet despite everything, there is beauty in being dust. Because Alcyoneus, for all its unimaginable size, did not announce itself. It did not demand attention. It existed silently, stretching across millions of light-years, until a species of specks on a small planet learned how to listen to the universe in new ways. We are the ones who found it. That fact matters. Not cosmically, perhaps, but meaningfully. In a universe indifferent to observation, observation itself becomes extraordinary. We built instruments sensitive enough to detect whispers from billions of years ago. We learned to interpret faint radio signals as evidence of colossal structures. We dared to measure something that dwarfed our ability to emotionally process it. Alcyoneus does not care that we know it exists, but we do, and that knowledge expands us in ways no physical structure ever could. The Speck realization is not an ending. It is a beginning. It strips away illusions of centrality, but replaces them with something quieter and more profound. Participation. We are not rulers of the universe. We are witnesses to it. As we dive into the anatomy of this 16 million light-year-wide monster-rich jets, its lobes, its environmental. Remember what makes this moment remarkable. Not the size of Alcyoneus, but the fact that something so small could understand something so large. That is the real miracle. For decades, the hierarchy of the universe felt comfortably settled. In astrophysics departments, conference halls, and peer-reviewed journals, there was a quiet consensus about the upper limits of galactic size. One name consistently occupied the throne, IC 1101, situated at the gravitational heart of the Abell 2029 galaxy cluster. IC 1101 was not merely large, it was excessive, a supergiant elliptical galaxy. It represented the most extreme outcome of galactic evolution that scientists could reasonably imagine. IC 1101 was thought to be the final form of a galaxy that had done everything right to grow large. Over billions of years, it had cannibalized neighboring galaxies, absorbing their stars and dark matter in repeated mergers. Each collision made it larger, heavier, and older, until it became a vast, golden sphere, dominated by ancient, red stars. It no longer formed new suns. It simply existed as a relic of cosmic accumulation. This galaxy did not just exceed expectations, it defined them. It stretched the models of galactic growth to their breaking point, while still remaining theoretically defensible. IC 1101 felt like a warning sign posted by the universe itself. This far, and no farther. Anything larger seemed incompatible with gravity, energy balance, or the accelerating expansion of space. To look at IC 1101 was to believe that cosmic growth had a natural endpoint. It was the ultimate monument to scale through mass, a silent titan that convinced astronomers they had finally found the ceiling. The reputation of IC 1101 rested not on mystique, but on numbers that were almost hostile to comprehension. With a diameter of roughly 4 million light-years, it dwarfed every galaxy previously measured. For context, the Milky Way spans about 100,000 light. Andromeda, slightly larger, stretches to around 220,000. IC 1101 made both of them look like minor features rather than major structures. If IC 1101 were placed in our local cosmic neighborhood, the comparison would be almost absurd. It would not merely brush against the Milky Way or Andromeda, it would engulf them entirely, consuming the space between as if distance itself were optional. The entire local group of galaxies would exist well inside its boundaries. Reduced to internal details, this scale gave IC 1101 a special status. It was not just the largest known galaxy, it was treated as a physical limit. The prevailing assumption was that gravity could only gather so much matter into a single cohesive structure before running into insurmountable constraints. Eventually, nearby material would be exhausted, expansion would win, growth would stall. IC 1101 appeared to sit exactly at that threshold, large enough to feel impossible, yet still explainable. It became the benchmark against which all future discoveries were measured and found lacking. No matter how impressive a new galaxy seemed, it was always smaller, tighter, more restrained. IC 1101 didn't just hold the record, it defined what a record could be. With IC 1101 firmly established at the extreme edge of known scale, the scientific community grew comfortable, not complacent, but confident. The universe might be vast, even infinite, but its structures appeared to follow predictable statistical patterns. Most galaxies clustered around average sizes. A few grew larger. One IC 1101 stood alone at the tail end of the distribution. This fit neatly into theoretical expectations. Bell curves are reassuring. They imply order, even when dealing with chaos. IC 1101 was seen as a rare but acceptable anomaly, a once-in-a-cosmic age outcome of unusually favorable conditions. Its existence didn't break the rules. It merely tested them. For nearly 30 years, this worldview held. IC 1101 became the default answer to a deceptively simple question. What is the biggest galaxy in the universe? It appeared in textbooks, lectures, documentaries, and exam questions. Every newly discovered giant was compared to it like a challenger stepping into a ring with a reigning champion, and every time, the challenger lost. The King of the Cosmos title wasn't official, but it was implicit. IC 1101 stood as the symbolic endpoint. A reminder that while the universe was capable of grandeur, it was still constrained. Growth had limits. Scale had boundaries. Or so it seemed. What made the eventual dethroning so dramatic was not that IC 1101 was wrong, but that it had been right for so long, long enough to feel permanent. Science, however, is not a monarchy. It does not respect reigns or legacies. It respects evidence. And in 2022, evidence arrived not from a deeper look in visible light, but from an entirely different way of seeing the universe. The turning point came with LOFAR, the low-frequency array, a sprawling network of radio antennas spread across Europe. Unlike traditional telescopes that focus on visible or infrared light, LOFAR was designed to detect faint, low-frequency radio emission signals produced not by stars, but by energetic processes acting over enormous distances. This shift mattered. Optical astronomy excels at revealing bright, compact objects. Radio astronomy, by contrast, is sensitive to the diffuse, the ancient, and the overlooked. It exposes structures that are spread so thin they barely interact with light at all. LOFAR wasn't hunting for records. It was mapping the radio sky methodically, cataloging emissions that most surveys had ignored. Its strength was patience and sensitivity, not spectacle, and that is precisely why it succeeded. By expanding our sensory range, LOFAR quietly undermined decades of assumptions. It suggested that the universe might be filled with colossal structures that were never invisible, only unseen. IC 1101's dominance had depended on where we were looking. LOFAR changed the question from what is the biggest thing we can see, to what have we been missing. LOFAR's mission was to uncover the universe that doesn't announce itself. Cold gas drifting between galaxies. Magnetic fields stretched across intergalactic voids. Ancient plasma clouds that glow not with heat, but with motion and charge. This was the domain of whispers rather than fireworks. During a routine survey, researchers noticed something unusual in a region of space roughly 3 billion light-years away. At first glance, The data looked unremarkably faint smudge of radio emission, barely distinguishable from background noise. No dramatic flare, no sharp boundaries, nothing that screamed discovery. And that was the problem. The signal was too extended, too coherent, too persistent to dismiss. It didn't match the signature of a typical radio source, nor did it align with known catalogued objects. It lingered in the data like a question that refused to go away. The team wasn't chasing giants. They were mapping, but mapping requires honesty, and honesty requires stopping when something doesn't fit. Slowly, carefully, they began to isolate the signal, clean the noise, and cross-reference distances. What emerged was unsettling. This was not a familiar object behaving strangely. It was something unfamiliar behaving consistently, and consistency, in science, demands attention. As analysis continued, skepticism dominated the early discussions. The structure appeared elongated, far too elongated. One obvious explanation was coincidence. Multiple radio sources aligned by chance, along the same line of sight. Another possibility was gravitational lensing, where mass bends space and distorts background signals into misleading shapes. These explanations were comforting. They preserved existing models. They suggested the universe was still behaving as expected, but the data refused to cooperate. As researchers refined the measurements and confirmed distances, those explanations fell apart. The emission was continuous. Its morphology was coherent. Its scale remained absurd, no matter how the numbers were adjusted. There were no breaks, no overlapping distances, no signs of distortion artifacts. This was not many objects pretending to be one. It was one object pretending to be impossible. At its center sat a single host, galaxy unremarkable in visible light. Modest in size, easily overlooked. Yet from it extended enormous lobes of radio-emitting plasma, stretching across space with an indifference to scale that defied precedent. The realization was slow and deeply uncomfortable. If this structure was real land, all evidence suggested it was then something larger than IC1101 existed, not slightly larger, categorically larger. And with that realization, the throne began to crack. The name Alcyoneus was chosen deliberately. In Greek mythology, Alcyoneus was a giant of immense strength, rendered immortal so long as he remained on his native ground. It was a fitting metaphor. This galaxy had grown not through violent wandering, but through long-term stability, remaining embedded in an environment that allowed it to expand unchecked. As measurements solidified, the implications became unavoidable. IC1101, long considered unassailable, was no longer the largest known galaxy. The crown did not shatter dramatically. It slipped quietly, almost politely, from one giant to another. This transition carried symbolic weight. IC1101 represented growth through mass and mergers. Alcyoneus represented growth through endurance and energy. They were giants, built by entirely different mechanisms. The dethroning was not an embarrassment for astronomy, was a revelation. It showed that our previous king was never wrong, only incomplete. IC1101 ruled a universe defined by starlight. Alcyoneus ruled a universe defined by motion, plasma, and time. The hierarchy hadn't collapsed. It had evolved. When the final measurements were confirmed, the numbers landed like a shockwave. Alcyoneus was not merely larger than IC1101. It was 4 times larger. While IC1101 spanned roughly 4 million light-years, Alcyoneus stretched an almost incomprehensible 16.3 million light-years from end to end. This was not an incremental improvement. It wasn't a narrow victory or a technicality. It was a demolition. The scale difference forced astronomers to pause not in celebration, but in recalibration. Entire frameworks for galactic size suddenly felt inadequate. The question was no longer which galaxy is the biggest, but how wrong were we about what big even means. Alcyoneus didn't just break a record. It broke a category. To understand the magnitude of this leap, metaphor becomes unavoidable. If a typical galaxy is a house, and IC1101 is the tallest skyscraper on Earth, then Alcyoneus is a structure that rises halfway to the moon. This isn't poetic exaggeration. In cosmic terms, a 4-fold increase in size is seismic. Astronomy rarely deals in such leaps. Discoveries tend to refine, not overthrow. Alcyoneus did the opposite. It suggested that previous assumptions about maximum galactic scale weren't slightly flawed. They were fundamentally incomplete. IC1101 had once marked the edge of possibility. Alcyoneus erased the edge entirely. The fall of the king wasn't just about size. It was about type. IC1101 is an elliptical, galaxy, a dense, glowing sphere of stars. Its boundaries are defined by starlight. Where the stars end, the galaxy ends. Alcyoneus plays by different rules. It is a giant radio galaxy. Its size is not determined by stars, but by energy, by motion, by breath. Its supermassive black hole drives twin jets of plasma outward, carving a territory through intergalactic space that no star could survive in. IC 1101 is massive. Alcyoneus is expansive. This distinction forced a fundamental question: what is a galaxy? If we only counted stars, Alcyoneus would appear large but ordinary. But its enormous radio lobes are physically connected to its core, energized by the same black hole, evolving as part of a single system. These lobes are not decorations. They are anatomy. Alcyoneus demanded that astronomers redefine galactic boundaries not by light alone, but by energy, magnetism, and motion. A galaxy, it turns out, is not just what shines, it is what reaches. When the discovery was published, the reaction was immediate. IC 1101 had not been surpassed, quietly it had been eclipsed. The fall of the king became emblematic of modern astronomy. Not because IC 1101 was wrong, but because our methods had been incomplete. Alcyoneus had always been there, broadcasting faint radio whispers into space. We simply weren't listening. The implication was sobering. The universe may be filled with giants we've overlooked not because they're rare, but because they don't glow. Alcyoneus also reignited debates about the cosmic web. At 16 million light-years wide. This galaxy is no longer just a node in the web, it is a thread. Its radio lobes are long enough to bridge intergalactic gaps, potentially influencing environments far beyond its stellar core. Alcyoneus blurs the line between galaxy and structure, between object and environment. It doesn't just exist within the universe's framework. It participates in shaping it. Then there is the question of age. To grow this large, Alcyoneus had to survive for billions of years, without interruption. It endured the violent mergers of the early universe and emerged into a quieter cosmic era, where it could expand slowly, patiently, and continuously. Its size is not the result of chaos but of stability. Alcyoneus is not young, explosive, or desperate. It is ancient. And it had time. Comparisons between IC 1101 and Alcyoneus are often framed as mass versus volume. IC 1101 likely contains more stars. It is dense, heavy, compact. Alcyoneus, by contrast, is vast but airy. Its volume dominated by thin plasma rather than matter, but scale perception favors space over weight. Alcyoneus feels larger because it occupies more of the universe. Its footprint is impossible to ignore. In the language of awe, volume wins. Perhaps most unsettling is where Alcyoneus lives. IC 1101 sits in a crowded galaxy cluster, surrounded by resources. Its growth makes sense. Alcyoneus does not. It is relatively isolated. It grew 4 times larger, with fewer materials, fewer mergers, fewer obvious advantages. This defies the logic of accumulation, with thought-governed cosmic growth. It is a giant that should not exist, and yet does. There is also a psychological shift. IC 1101 felt distant, static, safe. Alcyoneus feels alive. Its radio lobes resemble wings, lungs, or grasping limbs. It feels active, ongoing, like something that is still expanding, still claiming space. It is not just large, it is reaching. This discovery forced textbooks to change. Students who once memorized IC 1101 as the largest known galaxy now learn a new name. Alcyoneus becomes the new benchmark, the new final boss of cosmic scale. And even that title comes with an asterisk, because history suggests it won't last. The fall of IC 1101 was not a loss for science. It was a victory. It proved that the universe still holds surprises capable of humbling us. That our perceived limits often reflect our tools, not reality. Before LOFAR, Alcyoneus was invisible. Now it defines the horizon. What else are we missing? Ultimately, this transition marks a deeper shift. From a universe of stars to a universe of energy. The most significant structures may not be those that shine brightest, but those that reach furthest. Alcyoneus now sits on the throne, a 16 million light-year wide monument to unseen forces. And in its shadow, the Milky Way becomes not just a speck among stars, but a speck within the space that giants have claimed. To understand Alcyoneus, we must begin by dissecting its anatomy, starting at its visible heart and working outward toward its invisible, sprawling limbs. At the very center of this 16.3 million light-year wide structure lies a host galaxy, technically ordinary by optical standards. Viewed through a traditional telescope, it appears as a relatively unremarkable elliptical galaxy, a dense congregation of aging reddish stars, long past their star-forming youth. There are no glowing nebulae, no dramatic spiral arms, no fireworks of stellar birth. It looks quiet, even dull. And yet, this modest core functions as the control center for one of the largest coherent structures ever discovered. In proportion, the host galaxy is almost comically smaller, that at the center of an immense, invisible architecture. But scale is deceptive. Just as the human brain occupies only a small fraction of the body, yet governs everything it does. This galactic nucleus orchestrates the behavior of a structure millions of light years across. The apparent insignificance of the host galaxy is precisely what makes Alcyoneus so unsettling. From something so visually unassuming emerges a system capable of reshaping vast regions of intergalactic space. The true source of Alcyoneus's power lies buried deep within this central hub. At the galaxy's core resides a supermassive black hole, an object millions to billions of times more massive than the Sun. While nearly all large galaxies contain such black holes, the one anchoring Alcyoneus is not dormant. It is an active galactic nucleus, or a GN, meaning it is actively consuming matter and releasing enormous amounts of energy in the process. This black hole is not simply a sink where matter vanishes. As gas, dust, and even stars fall toward it, they form a rapidly spinning accretion disk. Friction and compression heat this material to extraordinary temperatures, causing it to radiate fiercely. Over billions of years, this black hole has acted as a long-running engine, steadily converting in falling matter into outward energy. What makes this especially important is duration. Alcyoneus's black hole did not flare briefly and fade. It remained active long enough to sculpt structures millions of light years long. The anatomy of the giant begins here not with size, but with sustained power generation on timescales that dwarf human history. The defining feature of Alcyoneus's anatomy emerges when the black hole fails to finish its meal. As matter spirals inward, approaching the event horizon, it accelerates to near light speeds. The intense motion generates powerful magnetic fields, twisted and amplified by the black hole's rapid spin. These magnetic fields act like cosmic funnels, channeling energy away from the center, rather than allowing it all to be swallowed. The result is the formation of relativistic jets, narrow, focused streams of plasma ejected from the black hole's poles. These jets are the arteries of the giant, transporting energy outward from the core into the surrounding universe. Instead of consuming everything, the black hole expels a significant fraction of its fuel back into space, transformed into motion and radiation. This process defies everyday intuition. Black holes are famous for what they take, not what they give back. Yet in systems like Alcyoneus, the outflow dominates the story. The jets carry the black hole's influence far beyond the galaxy itself, initiating the growth of structures that extend millions of light years into intergalactic space. The jets launched from Alcyoneus's central black hole are among the most powerful directional forces in the known universe. They erupt from the poles of the black hole, perpendicular to the plane of the host galaxy, forming two narrow beams of plasma moving at up to 99.9% the speed of light. These are not explosions. They are sustained, focused outflows, maintained over immense periods of time. To visualize their power, imagine a lighthouse beam, but replace light with a torrent of charged particles. These jets do not gently drift outward. They punch through the surrounding galactic gas with ease, carving straight paths through material that would stop almost anything else. Once launched, the jets embarked on journeys lasting millions of years, maintaining coherence over distances that dwarf entire galaxies. What makes this extraordinary is their stability. In many systems, jets wobble, bend, or dissipate. In Alcyoneus, they remained remarkably straight and focused, allowing energy to be transported far beyond the host galaxy. These jets are the delivery system that makes Alcyoneus's colossal size possible. Eventually, even jets this powerful encounter resistance. Space, contrary to popular belief, is not perfectly empty. It contains the intergalactic medium, an extremely thin but very hot gas that fills the voids between galaxies. When Alcyoneus's jets collide with this medium, they begin to slow, lose focus, and spread outward. This interaction marks the birth of the galaxy's most dramatic anatomical features, its radio lobes. The jets slam into the surrounding gas, creating shockwaves that force the energized plasma to billow outward in vast chaotic structures. The process is comparable to a high-pressure hose hitting a wall, where the narrow stream suddenly explodes into a wide turbulent spray. These collisions don't stop the flow of energy, they redistribute it. The momentum carried by the jets inflates enormous clouds of plasma, pushing against the surrounding universe. This is where Alcyoneus stops being a linear phenomenon and becomes a truly three-dimensional structure, expanding sideways as well as outward. The result of this expansion is the formation of the radio lobes, the colossal wings, that give Alcyoneus its record-breaking dimensions. These lobes are vast clouds of energized plasma, extending millions of light-years away from the central galaxy in opposite directions. Compared to the host galaxy, which spans only a few 100,000 light, the lobes are titanic. When astronomers measure Alcyoneus at 16.3 million light-years, they are not measuring stars. They are measuring the distance from the farthest edge of one radio lobe to the farthest edge of the other. This distinction is crucial. The galaxy's true body is not its stars, but the energy it has expelled into the universe. Mapping structures this large challenges conventional techniques. The lobes are diffuse, faint, and invisible to optical telescopes. Yet in radio wavelengths, they dominate the sky. Alcyoneus is not a star-defined giant, it is an energy-defined one, and the lobes are its most visible expression. The glow of Alcyoneus's lobes is produced by a process known as synchrotron radiation. This occurs when charged particles, primarily electrons, are forced to spiral around magnetic field lines at relativistic speeds. As they curve through space, they emit energy, not invisible light, but in radio waves. This is why Alcyoneus remained hidden for so long. To the human eye, the lobes are completely invisible. There is no glow, no color, no outline, but to a radio telescope, they blaze brightly, revealing a structure that dominates its surroundings. Synchrotron radiation also encodes valuable information. By analyzing the frequency and intensity of the radio waves, astronomers can infer the strength of magnetic fields, the energy of particles, and even the age of different regions within the lobes. In this way, the radio glow is not just a signal, it is a diagnostic tool, allowing scientists to read the internal history of the giant. One of the most puzzling aspects of Alcyoneus's anatomy is the extraordinary collimation of its jets. In most radio galaxies, jets lose focus as they travel, spreading out and dissipating relatively quickly. Alcyoneus's jets do not. They remain tightly confined for millions of light-years before finally blooming into massive lobes. This suggests an unusual degree of magnetic stability. The jets appear to be guided by exceptionally well-organized magnetic fields, preventing them from unraveling or leaking energy prematurely. Some researchers describe this as the galaxy having a kind of spine, a structural backbone that maintains alignment across cosmic distances. How such stability is achieved remains an open question. Theoretical models struggle to explain how magnetic fields can remain coherent over such immense scales. Alcyoneus therefore represents not just an extreme example, but a challenge to existing physics, pushing models of jet formation and propagation to their limits. Despite their enormous size, the radio lobes of Alcyoneus are astonishingly empty. The plasma within them is billions of times less dense than the air you are breathing. In practical terms, they are almost perfect vacuums, lightly seasoned with charged particles and magnetic fields. If a spacecraft were to pass through a lobe, it would encounter no resistance. There would be no sensation of movement, no visible clouds, no collisions with particles. And yet, the spacecraft would be immersed in a region humming with energy, radio waves, and invisible magnetic forces. This paradox, vast structures made of almost nothing, is central to understanding Alcyoneus. Its size is not achieved through mass, but through reach. The lobes occupy enormous volumes of space precisely because they are so light, able to expand freely into the low-density regions of the universe. The sheer scale of Alcyoneus's lobes turns them into cosmic time capsules. Plasma at the outer edges of the lobes was expelled millions, sometimes tens of millions, of years ago. The closer one looks to the center, the younger the material becomes. By studying variations in radio frequency across the lobes, astronomers can reconstruct the activity history of the central black hole. Regions of brighter emission indicate periods of intense feeding, while fainter zones mark quieter In effect, the lobes preserve a layered record of the black hole's life. This allows scientists to do something remarkable. Read the biography of a black hole written across millions of light. Alcyoneus is not frozen in time, it is a living archive, storing evidence of its own growth in the structure of its anatomy. A natural question arises. What keeps these immense lobes from drifting away into space? The answer lies in pressure balance. Inside the lobes, Hot plasma pushes outward. Outside, the intergalactic medium pushes back. Alcyoneus exists as a gigantic bubble, inflated by energy, but confined by its surroundings. The pressure of the external medium, though extremely low by human standards, is sufficient on cosmic scales to contain the lobes and maintain their shape. Magnetic fields further reinforce this containment, acting like tensioned membranes that resist collapse. This balance is delicate. Too little external pressure, and the lobes would disperse. Too much, and they would be crushed. Alcyoneus occupies a rare sweet spot, where expansion and confinement remain in equilibrium over billions of years. Within the lobes lie regions known as hotspots, compact areas where the jets are actively colliding with the intergalactic medium. These are the front lines of Alcyoneus's expansion, where kinetic energy is converted into heat, radiation, and shockwaves. In Alcyoneus, these hotspots are found millions of light years from the central galaxy, a clear sign that the black hole's influence extends astonishingly far. The engine is not a relic of the past. It remains capable of driving energy across vast cosmic distances. Hotspots also provide critical clues about directionality and timing. Their locations reveal where the jets are currently depositing energy, offering snapshots of the giant's ongoing growth. Between the central galaxy and the outer lobes lies a region filled with older, fading plasma. These cocoons are the remnants of previous outbursts, material expelled long ago that now drifts and cools. This region is not empty. It forms a specialized environment, saturated with magnetic fields and high-energy particles. For smaller galaxies passing through, this can be hostile terrain, inhibiting star formation and stripping gas. In this sense, Alcyoneus does not merely exist in space, reshapes it. It alters the conditions of its surroundings on enormous scales, effectively terraforming intergalactic space into an energetic wasteland. The magnetic fields threading Alcyoneus are among its most important anatomical features. These fields are stretched, twisted, and amplified by the motion of plasma, forming a vast magnetic skeleton that gives the lobes coherence and shape. The scale of these fields is staggering. They span millions of light years and may influence the paths of cosmic rays, traveling across entire regions of the universe. In effect, Alcyoneus could act as a giant magnetic lens, subtly altering the trajectories of high-energy particles far beyond its visible boundaries. These fields are not passive. They store energy, guide motion, and help maintain the structure of the giant itself. When compared to IC1101, the anatomical differences are striking. IC1101 is a galaxy of mass-dense, star-packed body anchored by gravity. Alcyoneus is a galaxy of motion and field. It behaves less like a solid object and more like a cosmic storm. Its structure is defined by flows, pressures, and magnetic tension rather than stellar density. This difference explains why Alcyoneus can grow so large. Stars are heavy. Plasma is light. Energy, when given enough time and space, can travel much farther than matter. The airy nature of Alcyoneus's lobes is what allows it to achieve such extreme size. Because the plasma is light, it can expand into low-density regions of the universe without being torn apart. If Alcyoneus lived in a crowded cluster like IC1101, its lobes would be disrupted, crushed, or stripped away by gravitational interactions. Instead, it resides in a relative cosmic desert. Alcyoneus is not just large because of power, it is large because of isolation. Perhaps most puzzling is the nature of the host galaxy itself. Despite producing the largest known radio structure in the universe, the host galaxy appears surprisingly ordinary. It lacks vast gas reservoirs or extreme star formation. This mismatch between modest host and extreme output is known as the Alcyoneus paradox. It challenges assumptions about how much fuel is required to sustain such enormous jets. The engine seems vastly overpowered relative to its environment. Some researchers suggest Alcyoneus represents a perfect storm of conditions. The central black hole may be spinning near the theoretical maximum, extracting rotational energy with extreme efficiency. Alternatively, the surrounding intergalactic medium may be unusually thin, offering almost no resistance to expansion. Most likely, it is a combination of factors, environment, and physics aligning just right. Alcyoneus may be a cosmic mutation, rare, unstable, and revealing what is possible under extreme conditions. Alcyoneus also challenges how we think about connectivity. Its components are separated by millions of light years, yet they function as a single system. The jets link the black hole to the lobes. Magnetic fields tie the lobes back to the core. Energy flows continuously across distances so vast they defy everyday definitions of unity. Alcyoneus is not a collection of parts. It is an organism of energy. In the end, Alcyoneus serves as a bridge between scales. It connects black hole physics to the cosmic web, the microscopic to the macros, COPIC. That it proves that energy, not just matter, sculpts the universe. Stars mark beginnings, but radio waves trace influence. Alcyoneus stretches 16 million light-years not to impress, but because the universe allowed it to, and in doing so, it reveals that the true architecture of the cosmos is written not in light but in motion. Field and power. Numbers like 16.3 million light-years sound impressive, but they are functionally meaningless to human intuition. Our brains evolved to judge distances relevant to survival: the length of a valley, the height of a tree, the journey between water sources. Even a few hundred miles strain instinctive understanding. When confronted with distances measured in millions of years at the speed of light, comprehension collapses. The number becomes symbolic rather than informative. This is why scale comparisons matter. They translate abstraction into experience. To understand Alcyoneus, we must build a ladder of familiarity. Starting with what feels large to us and stepping outward, layer by layer, each rung destabilizes the last, forcing recalibration. Eventually, the ladder rises high enough that the mind rebels not because the comparison fails, but because it succeeds. That moment of rebellion is the only honest response to a structure that exists beyond evolutionary sense. Begin with the Milky Way, our home. Baseline for large, it spans roughly 100,000 light-years and contains hundreds of billions of stars, many with planets of their own. From within, it feels boundless. To create an intuitive model, imagine shrinking the Milky Way down to the size of a glowing dinner plate resting on a table. On that same scale, the Andromeda Galaxy, our nearest major neighbor, would be about 25 feet away. That gap feels enormous. It reinforces the idea that galaxies are isolated islands, separated by vast emptiness. This mental model is comfortable. It aligns with how we imagine the universe: spacious, sparse, and orderly. At this point, the Milky Way still feels appropriately grand. It still feels like a meaningful unit of scale. That sense does not survive the next step. Now introduce Alcyoneus into this model. If the Milky Way is a dinner plate, Alcyoneus would stretch nearly 160 feet, from end to end, longer than a professional basketball court. Suddenly, the Milky Way stops feeling like a galaxy and starts feeling like debris. Standing at one end of Alcyoneus, the Milky Way would be a faint glimmer far away, barely registering in peripheral vision. This is not a comparison between big and bigger. It is a comparison between different classes of existence. One object defines a room, the other defines the building. Familiar reference points break down. The scale difference is so extreme that it forces a psychological downgrade of everything that came before. What once felt enormous becomes incidental. Next, consider the local group, our immediate galactic neighborhood. It includes roughly 50 galaxies, including the Milky Way, Andromeda, and Triangulum, all bound together by gravity. The entire local group spans about 10 million light. This feels appropriately large for a community of galaxies. It represents structure, interaction, and shared motion. Now compare that to Alcyoneus, which stretches 16.3 million light-years end to end. A single galaxy exceeds the size of our entire neighborhood. This comparison is deeply unsettling because it collapses hierarchy. Groups were supposed to be larger than individuals. Alcyoneus reverses that expectation. It does not fit neatly into the cosmic filing system we rely on. Instead, it overwrites it. If Alcyoneus were placed into our region of space, it would behave less like a galaxy and more like infrastructure. One end of its radio lobes could lie near the Milky Way, while the other would stretch far beyond Andromeda into the surrounding local void. Regions of space we consider remote would suddenly be connected by a single, coherent structure. Alcyoneus would act as a cosmic bridge, linking environments that normally never interact directly. This is where scale becomes functional rather than descriptive. Alcyoneus doesn't just occupy space, it alters connectivity. It performs a role usually reserved for clusters or filaments, yet it does so alone. That contradiction is the core of its shock value. This bizarre scale becomes clearer when we examine what actually defines the size of a galaxy. In the Milky Way, size is dictated by stars. Where the starlight fades, the galaxy ends. Alcyoneus ignores this rule. Its stellar component is relatively modest, a faint core, compared to its vast extent. The true bulk of the galaxy is plasma, not stars. Two enormous radio lobes extend roughly 8 million light-years, in opposite directions, dwarfing the stellar body between them. From afar, the stars appear as an afterthought, a candle between two glowing clouds of energy. Alcyoneus forces a redefinition of galaxy itself. It is not light, it is energy, and energy scales differently than matter. An anatomical metaphor helps. Imagine a bird with the body of a sparrow but wings stretching miles in either direction. Such a creature would defy biology. Its proportions would be nonsensical. That is exactly the reaction astronomers had when they first measured Alcyoneus. The host galaxy, the body is ordinary. The radio lobes, the wings are not. They stretch far beyond anything expected from standard galactic evolution. Astronomers are accustomed to proportional growth. Alcyoneus is not proportional. It is exaggerated to the point of absurdity. That violation of expectation is what made the discovery so disruptive. It wasn't just larger than predicted. It was structurally wrong. Speed provides another perspective. At the speed of light, you could reach the moon in seconds and the sun in minutes. Crossing the Milky Way would take 100,000 years already, a number that strains intuition. Most people stop there. Alcyoneus does not allow that comfort. To cross it at light speed would take 16.3 million years. Even the fastest possible motion permitted by physics fails to make the structure feel manageable. Alcyoneus exists on a timescale where travel becomes history. Distance turns into deep time. Motion becomes memory. Scale ceases to be spatial alone and becomes temporal as well. 16 million years ago, Earth was in the Miocene epoch. Early apes were beginning to diversify. The Himalayas were still rising. Grasslands were spreading across continents. If a signal had been sent from one end of Alcyoneus during that era, it would only now be reaching the other end. This means Alcyoneus is so large that its extremities exist in different chapters of planetary history. Its limbs are out of sync with one another. Within a single galaxy, cause and effect are separated by epoch. That alone pushes Alcyoneus beyond anything we intuitively classify as a single object. Volume adds another layer of discomfort. If the Milky Way were reduced to a single drop of water, Alcyoneus would not be a bucket, it would be a swimming pool. The amount of intergalactic space enclosed within its radio lobes is staggering. In theory, thousands of Milky Way-sized galaxies could fit inside that volume without touching. Most of this space is empty, but it is not neutral. It is permeated by magnetic fields, radiation, and pressure gradients shaped by Alcyoneus itself. The galaxy does not just exist within the void. It claims it. It turns emptiness into territory. Galaxy clusters are often described as the largest gravitationally bound structures in the universe. They contain thousands of galaxies and span roughly 10 to 20 million light. Alcyoneus, a single galaxy, occupies comparable dimensions. This comparison borders on offensive to intuition. What normally requires the combined mass of trillions of stars has been achieved here through sustained energy output from one central black hole. Alcyoneus compresses the role of a cluster into a single entity. It demonstrates that energy, applied patiently, can rival mass in shaping the universe. This is where awe shifts toward existential discomfort. When placed beside Alcyoneus, the Milky Way no longer feels large. It feels fragile, temporary. If the universe is an ocean, the Milky Way becomes a life raft, self-contained, but insignificant, while Alcyoneus is a continent. This does not diminish our home's beauty, but it strips away illusions of scale-based importance. Familiarity, not size, is what made the Milky Way feel vast. Alcyoneus exposes that bias. A light year equals roughly 6 trillion miles. These units quickly exceed usefulness. The Milky Way spans hundreds of quadrillions of miles. Alcyoneus approaches 100 quintillion. These numbers exist outside commerce, engineering, and everyday science. They live in a realm where only mathematics and cosmology operate comfortably. At this scale, size becomes abstract, yet remains physically real. The universe does not care whether we can picture it. The cosmic web resembles a vast network of filaments and voids. Most galaxies are tiny beads along these strands. Alcyoneus is different. It is large enough to be part of the filament itself. It doesn't merely occupy a node, contributes to the structure. That places Alcyoneus in a rare category, not just an object within large-scale structure, but an element of it. Voids are supposed to be empty, millions of light-years of nothing. Near Alcyoneus, even nothingness is occupied. Its radio lobes fill regions that would otherwise be silent. This challenges the idea that empty space is truly empty. Near a giant radio galaxy, emptiness becomes saturated with influence. The energy required to inflate lobes this large is immense, equivalent to billions of supernovas sustained over millions of years. By comparison, the Milky Way's black hole is quiet. Alcyoneus is not whispering. It is broadcasting across intergalactic space. Scale also breaks communication. A civilization on one side of Alcyoneus could never meaningfully communicate with one on the other. By the time a message arrived, stars would have evolved or died. Alcyoneus is so large that it is temporarily disconnected from itself. Even compared to enormous structures like the Hercules Corona Borealis Great Wall, Alcyoneus stands apart. The wall is a crowd. Alcyoneus is an individual. It is the largest single connected galactic structure known an outlier among outliers. The final realization is simple and unsettling. The universe has no known maximum size, only a maximum size observed so far. Alcyoneus turns the Milky Way into a speck, history into a blink, and certainty into a moving target. And yet, we measured it. Tiny beings on a small planet dared to map a giant. That, perhaps, is the most profound scale comparison of all. The discovery of Alcyoneus is not merely a record-breaking curiosity meant to decorate astronomy textbooks. It represents a genuine crisis for modern astrophysics. When an object exceeds theoretical expectations by a factor of 4, the problem is not a rounding error, it's conceptual. Our simulations of galaxy evolution, refined over decades and tested against countless observations, simply do not predict a structure like this. According to those models, Alcyoneus should never have formed, let alone survived. Its existence implies that something fundamental is missing from our understanding of how galaxies grow, how energy propagates through space, or how long cosmic engines can remain active. In science, anomalies are not inconveniences. They point directly at the boundaries of knowledge. Alcyoneus is a 16 million light-year-long question mark written across the sky, forcing theorists to revisit assumptions that once felt secure. It tells us that the universe is not obligated to behave according to our equations, that those equations, no matter how elegant, are provisional. The first major puzzle is what astronomers call the host galaxy paradox. In most cases, extreme structures come from extreme origins. The largest radio galaxies usually reside in massive host galaxies, cosmic giants, swollen with stars, gas, and dark matter, anchored by black holes, billions of times the mass of the sun. Alcyoneus breaks that rule completely. Its host galaxy is surprisingly ordinary. It is not unusually massive, not especially luminous, and not surrounded by vast reservoirs of fuel. On its own, it would barely stand out in a catalogue of and yet, from this unremarkable core, extend the largest radio lobes ever observed. The mismatch is jarring. It is as if a standard garden hose was somehow responsible for flooding an entire continent. This paradox challenges the intuitive link between cause and effect in galaxy formation. How can something so average generate something so extreme? The disconnect suggests that we may be underestimating how efficiently black holes can convert modest resources into colossal influence. This paradox hints at a deeper truth. A galaxy's reach may not be strictly tied to its mass. For decades, astronomers assumed that a black hole's output was limited by its fuel supply. More gas meant more energy. Less gas meant less reach. Alcyoneus undermines that logic. If its host galaxy is average, then its fuel intake should also be average. Yet the scale of its radio lobes implies sustained, extraordinary power over immense timescale. One possible explanation involves black hole spin. If Alcyoneus's black hole is rotating near the maximum speed allowed by general relativity, it could tap into the rotational energy of space-time itself through a process known as frame. In this scenario, the black hole is not just burning fuel, it is extracting energy from the structure of space-time. This idea pushes black hole physics into an extreme regime, one rarely tested by observation. Alcyoneus may represent a case where geometry, not just mass, determines cosmic impact. Then there is the environment enigma. Most known galactic giants, such as IC 1101, live at the centers of dense galaxy clusters. These environments are rich in matter and gravitational interactions, providing ample fuel for growth. Alcyoneus does not share this advantage. It resides in a relatively sparse region of the cosmic web, a low-density filament far from the crowded hubs of galactic activity. This makes its size even more perplexing. In a cosmic desert, fuel should be scarce, interactions should be rare, growth should be limited. And yet, Alcyoneus developed the largest known galactic limbs in the universe. This contradiction suggests that environment may play a more nuanced role than previously thought. Rather than enabling growth through abundance, isolation may sometimes allow extreme expansion by removing obstacles. Alcyoneus forces us to rethink the relationship between richness and scale. One compelling idea is that Alcyoneus grew large, precisely because it lived in a cosmic desert. In dense clusters, the intergalactic medium is thick, turbulent, and chaotic. Jets fired from a galaxy's core encounter resistance almost immediately, compressing and confining the resulting lobes. But in a low-density environment, there is little to stop them. Alcyoneus's jets may have encountered almost no opposition, allowing them to coast outward for millions of light years. In this view, Alcyoneus is not exceptionally powerful. It is exceptionally unobstructed. Its size reflects not brute strength, but uninterrupted expansion. This reframes the galaxy not as a cosmic overachiever, but as a beneficiary of rare conditions. It suggests that the universe's emptiest regions may harbor its most extreme structures, simply because nothing stands in their way. This leads directly to implications for the cosmic web itself. The universe is structured like an enormous network of filaments composed of dark matter and gas, with galaxies forming at intersections. Traditionally, galaxies are treated as nodes on this web point, where matter accumulates. Alcyoneus complicates that picture. At 16 million light-years wide, it is no longer just a node. It is a structural component. Its radio lobes stretch across regions that were previously classified as voids, injecting energy and magnetic fields into areas assumed to be relatively empty. This means the spaces between galaxies may be far more dynamic than we believed. The cosmic web may not be a clean lattice of matter and emptiness, but a tangled system where energy from rare giants bleeds into the gaps, reshaping large-scale structure. Another enduring mystery is magnetic longevity. For radiolobes to remain visible, their electrons must continue spiraling along magnetic field lines. Over millions of light years and millions of years, those fields should weaken, tangle, or dissipate. Yet Alcyoneus's lobes remain crisp and coherent. This implies that some mechanism is actively sustaining or regenerating the magnetic fields far from the galaxy's core. One possibility is that the jets themselves act as magnetic dynamos, continuously reinforcing field structure as they travel. If true, this represents a form of energy transfer unlike anything we can reproduce on Earth. It suggests that the universe is capable of maintaining ordered, magnetic systems across distances that make our largest laboratory experiments seem microscopic. Alcyoneus may be demonstrating a fundamental process we have yet to fully understand. Why does any of this matter to us? Because Alcyoneus functions as an extreme physics laboratory that we could never hope to build. Inside its lobes, plasma obeys the same laws it does in fusion reactors or particle accelerators, but on scales trillions of times larger. By studying Alcyoneus, we are testing magnetohydrodynamics, relativity, and particle physics under conditions impossible to replicate on Earth. It allows us to observe how microscopic laws scale up into macroscopic consequences. The behavior of electrons near a black hole's event horizon ultimately shapes structures spanning millions of light years. Alcyoneus is the clearest demonstration yet that the universe operates as a continuous system, where the smallest scales can influence the largest. Alcyoneus also challenges our understanding of cosmic time to reach its current size. Its jets must have remained active and precisely aligned for a significant fraction of the universe's history. Most black holes are intermittent. They flare, quiet down, and reignite. Alcyoneus's central engine appears to have maintained remarkable stability across billions of years. This raises deep questions about angular momentum and alignment. How does a galaxy avoid wobbling, merging, or disrupting its jet orientation over such immense time stables? What stabilizing forces are at play? The mystery is not just how powerful the engine is, but how disciplined it has been. Beyond physics, Alcyoneus carries philosophical weight. Humanity has repeatedly been displaced from the center of the cosmic story. First Earth, then the Sun, then the Milky Way lost their privileged status. Alcyoneus continues that tradition. It shows that the most significant events in the universe, those involving the greatest transfers of energy, are happening far beyond human perception, in wavelengths we cannot see, in structures that make our entire history feel negligible. This is not a demotion. It is an invitation to humility. The universe is vast, active, and indifferent to our narratives. Alcyoneus is also valuable as a void probe. Its enormous lobes respond sensitively to the pressure of the surrounding intergalactic medium. By studying their shape and curvature, astronomers can infer the density and temperature of gas that would otherwise be invisible. In effect, Alcyoneus allows us to weigh emptiness. This has profound implications for cosmology. It reveals that the voids between galaxies are not truly empty, but filled with diffuse, pressurized material. Without giants like Alcyoneus, this hidden component of the universe would remain almost entirely unmeasured. The identity of Alcyoneus also forces a definitional crisis. What exactly is a galaxy? If we define it purely by stars, then Alcyoneus is modest. If we define it by gravitational and energetic influence, then its size explodes beyond anything in our catalogs. This distinction matters. It suggests that galaxies may possess vast, overlapping atmospheres of energy and magnetism that extend far beyond their visible boundaries. The universe may be less a collection of isolated islands and more a continuous field of interacting influence. There is also the question of the future. Because of light travel time, we see Alcyoneus as it was 3 billion years ago. In the present universe, it may be larger still, or it may be fading. The engine could have shut down, leaving its lobes to drift and dissipate into ghostly remnants. Alternatively, it may have collided with another structure or continued expanding unchecked. We are not watching a live event. We are examining a fossil caught mid-motion. The outcome remains unknown. Alcyoneus has also reignited interest in dark galaxies. If something this enormous could remain hidden simply because it emits little visible light, what else have we missed? Could there be structures composed almost entirely of dark matter, even larger than Alcyoneus? Its discovery marks a shift in astronomical strategy, from searching for what shines to searching for what displaces space itself. The feedback from Alcyoneus is immense. By pumping energy into the intergalactic medium, it heats gas across millions of light years, preventing it from cooling and collapsing into new stars. In this sense, Alcyoneus suppresses future galaxy formation around it. It is not just large, it is influential. It creates a kingdom of emptiness through sheer energetic dominance. Understanding this feedback is crucial. If many galaxies behave like Alcyoneus, the universe would be far hotter and far emptier. The fact that it does not suggests that Alcyoneus is an exception, not the rule. Discovering why it broke the pattern may explain why normal galaxies, like the Milky Way, were able to grow peacefully without being sterilized by their own black holes. Earlier, scale inspired wonder. Here, it inspires unease. Alcyoneus violates expectations so thoroughly that it feels almost unnatural. It reminds us that the universe is not obligated to be intuitive, comfortable, or comprehensible. Physics operates regardless of our ability to conceptualize it. That realization carries a quiet fear not of danger, but of irrelevance. Future instruments, such as the Square Kilometre Array, will probe the universe with even greater sensitivity. Many astronomers suspect Alcyoneus will not remain the largest known galaxy for long. The ceiling has been broken. The only question now is how high it truly is. Alcyoneus ultimately represents the age of discovery we are living in. Despite centuries of observation, the universe still hides its giants in plain sight. It reminds us that exploration is not finished, that the dark still holds surprises capable of rewriting textbooks. In the end, Alcyoneus is a mirror. It reflects our limitations, our curiosity, and our persistence. It teaches us that the universe is always larger, stranger, and more complex than we expect, and yet, we keep measuring. That impulse to understand what dwarfs us may be humanity's most cosmic trait.